Hello, everyone. My name is Wen Chen. I'm an assistant professor in the Department of Mechanical and Industrial Engineering at the University of Massachusetts Amherst. Today, I'm going to give a brief introduction to additive manufacturing and how this technology can be used for 3D printing of emerging complex alloys. As we all know, the increasing demand for materials are requiring materials to become more and more complex. This trend can be found in many examples, such as steels. For example, many years ago, steel was very simple, just iron and carbon, but nowadays steel can be very complex, composed of more than 10 elements, right? And as other structural materials such as dental alloys, aerospace superalloys, amorphous alloys, also called metallic glasses, and also some even functional materials such as thermoelectric materials. So these compositional complex alloys are sometimes also called high entropy alloys. Now, why do we like high entropy alloys? What's the benefit of high entropy alloy? So for students who may not be familiar with high entropy alloys, so let me give several minutes to give a very brief introduction of this alloy concept. So in a conventional alloy design approach, you take a measure element as a solvent, and then you dope small concentrations of solutes to form so-called dilute alloys. For example, if you want to make a soda, you take the tin as a solvent, and then you add a little bit amount of lead inside. So this gives you a soda alloy. If you want to make a bronze, you take a copper as the major element, which is the solvent, right? And then you dope small concentrations of tin and zinc inside. So this gives you bronze. So in a sense, these conventional dilute alloys are often located at the corners of the phase diagrams, right? In contrast, high entropy alloys are a family of alloys with multi-principal elements, which means that you can mix multiple elements all in significant proportions. For example, you can mix cobalt, iron, or nickel all in significant proportions near equiatomic ratios, so that this gives you high entropy alloy. So in this case, high entropy alloys allow us to explore a vast compositional space in the central region of the phase diagram. So besides the vast compositional space that we can explore in the central region of phase diagram, there's also a fundamental difference between the conventional dilute alloy and also the high entropy alloy in terms of crystal lattice structure. So in conventional dilute alloy, because it is based on one major principal element, so you don't see significant lattice distortion there. Whereas in high entropy alloys, which are composed of multiple principal elements, which may have quite different atomic radii, right? So this will give us severe lattice distortion along with very high entropy of mixing effect. So all these core features will need to sometimes, or most times, excellent material properties, including high strength, high toughness, and great creep resistance, and so on. So this is an example of HB material chart to show you fracture toughness versus yield strength for many structural materials, such as ceramics, polymers, conventional metal alloys, metallic glasses, and high entropy alloys. From this HB chart, you can see that high entropy alloys exhibit a great combination of high yield strength as well as great fracture toughness, right? So it is great that high entropy alloys enable us the great opportunity for a new material design in the enormous compositional space, right? But in the meantime, it also brings grand challenges in processing of these new materials by conventional manufacturing approaches. For example, if you do casting of high-chip alloys, you often end up with a lot of processing defects, such as the casting pores on the left side. Also, most often you will see very severe elemental segregation between the dendritic versus interdendritic regions. So these defects are largely due to the high viscosity of the high-chip alloys melt, also the different melting points among different constituent elements. So to address the issue, in the next, in this workshop, I will introduce how we can utilize additive manufacturing to fabricate emergent complex alloys. And in the first section, I will give a brief introduction to additive manufacturing. And then in the second section, I will give some case examples to show you how we can use laser additive manufacturing technology to produce complex alloys with engineered structures and excellent material properties. So first of all, let's look at what is additive manufacturing. So additive manufacturing, by definition, refers to a process by which digital 3D design data is used to build up a component in layers by depositing materials layer by layer. So the term 3D printing is also often used as the alternative to additive manufacturing, but in fact, the additive manufacturing is a more accurate term because it describes a professional production technique which clearly distinguished from conventional subtractive manufacturing processes where materials are removed layer by layer, right? So this is a more intuitive schematic, more intuitive images to show you how additive manufacturing contrasts to subtractive manufacturing. In subtractive manufacturing, on the left, you will see that such as where you use CNC machine in the machine shop, you will see that the material is removed layer by layer, and this is, you can treat it as a top-down approach. Whereas in additive manufacturing process, the material is deposited layer by layer. So this can be treated as a bottom-up process. So why do we like additive manufacturing? So I guess the most straightforward answer is that a lot of components cannot be made by conventional manufacturing, right? For example, this cup, if you want to use conventional machining approach, it's very difficult to achieve to make this cup. If you look at this cup carefully, you will see that the cavity of this cup may be too deep to machine by even conventional, the advanced CNC machine, and the undercut here cannot be performed without more than 3-axis machining, right? And the base of the cup cannot be machined because the machine must hold using a fixture, right? And some very intricate internal features, such as the sharp internal features, cannot be machined without a tool radius that is good enough to machine this radius, right? So these are all the challenges that you may face in a machine shop if you want to use CNC machine to make this cup. So now additive manufacturing provide us with new opportunities for faster prototyping, customized manufacturing, especially for components with complex geometries. And also, in addition, it will allow us for designing new materials with enhanced material properties. So now let's look at when is the first 3D printer was invented. So this can be traced back to 1980s. So in 1986, the first 3D printer was invented by Charles Hull. This 3D printer was actually a stereolithography technique. So it's called projection stereolithography. And then after this concept was invented in 1987, the first stirring lithography machine was made. And then later on, this technology got more and more attention. So on the right side, you can see how the first 3D printer looks like. So at that time, the stereolithography-based 3D printer was mainly used for polymer 3D printing. For example, these were the typical examples how projection stereolithography was used for making 3D polymer components. And this stereolithography technology was also called photopolymerization process. So in this case, essentially, a photosensitive polymer resin will be shot by a laser, and then it will solidify under exposure to the laser, and then solidify into a polymer bulk, right? So next, in the later slides, I will explain in detail how this process works. So now a question is, why is additive manufacturing progressing much more rapidly now versus 30 or 40 years ago? So if you look at the technology involvement, you will see that there are many advancements there in terms of both software and hardware. So certainly there's a wide availability of CAD and CAM software development in the past 30 or 40 years, right? This is very necessary for the development of additive manufacturing technology. And the second reason can be traced to the improved automation and component technologies. And then the third reason is a growing library of printable materials. So basically, there are a lot of materials study for additive manufacturing processes, which makes the material design for additive manufacturing more matured compared with 30 or 40 years ago. And in addition, you will see nowadays there are a lot of industry and government investment on the additive manufacturing technologies. And beyond that, we will also see a very important aspect is the freedom to operate enabled by patent expirations, because now you can see a lot of the old patents have been expired. So we have more freedom to do the R&D for additive manufacturing. So certainly there are also a strong momentum, confidence, and creative vision from both education and industry for these additive manufacturing technologies. So if you look at the additive manufacturing technology industry share market, you will see that in 2022, this additive manufacturing market has been increased to 14 billion US dollars. And in the past 2 years, it has also been steadily increased to $20 billion. And it has been also projected to continuously increase and along almost exponential trend. You will see that by projection to 2032, the additive manufacturing market will increase up to 90 billion US dollars. So this is really a huge number compared to conventional manufacturing. And also among additive manufacturing market, you'll see that the plastic additive manufacturing shares almost 50%, and then metals shares a dramatic percentage, almost 30 or even 40%, and then the rest is for the ceramics industry. And additive manufacturing have found profound examples in terms of industrial usage, and these are very typical examples where you can see additive manufacturing applications in various fields. For example, GE has announced their fuel nozzle fabrication by additive manufacturing, and also in the middle, in the upper middle figure, you will see this is an example where additive manufacturing can be used for making the injection mold, right? And on the right, upper right figure, you will see that additive manufacturing has been used for Nike shoe fabrication. And then at the bottom, you will see that additive manufacturing can be used for many functional parts, such as the antenna and biomedical implants, as well as the Google smartphone. Right? So in a typical additive manufacturing process, there are multiple steps. So the first step is to create a CAD file. And then the second step is to convert this CAD file into a so-called digital STL file, stereolithography file. And this STL file is then transferred to the machine. And then you set up the machine, and then you build a 3D component based on the 3D digital STL file. And then after you build the 3D component, you remove the component from the building substrate. And then, if necessary, you may sometimes apply some post-process, such as heat treatment. And then in the end, you can apply the application. Right? So in general, there are 5 different additive manufacturing methods. So these methods can be categorized into wet photopolymerization process, which is also called stereolithography process, as I just mentioned earlier. And the second technology is called inkjetting process. In this case, the ink droplets will be deposited drop by drop to form a 3D object onto the substrate. And the third technology is called a material extrusion-based technology, which sometimes you can find a very widespread use, such as FDM, fused deposition modeling, and direct ink writing. And the last 2 technology are called powder bed fusion and directed energy deposition. So these 2 technologies are 2 most common methods for metal 3D printing. So these 5 technologies are categorized based on the energy input. So from low energy density to high energy density, you can see the the sequence of the 5 different additive manufacturing technologies. So in the next few slides, I will show you very brief videos for each technology to show you how the work principle for each additive manufacturing technology. So the first is so-called wet photopolymerization process, also called projection stereolithography. So how does this process work? So you can see this video. Okay, so this is a video from Photo Labs. So in this video, as it shows, so basically the photosensitive resin is exposed to a laser. Under exposure, it will be solidified. So when you expose the resin layer by layer, you can build a 3D polymer structure layer by layer. So the next 3D printing technology is so-called inkjet printing. So let's see how this technology works. Okay, so as you can see, this technology is based on a droplet inkjet process, right? Droplet by droplet. And the next technology is extrusion-based technology. So it's called fused deposition modeling, or sometimes direct ink writing shares a similar principle. So this is a video taken from my own research group. So you can see in this case, an ink is extruded from a nozzle, and upon extrusion, the ink can retain the shape. You can build an overhang structure layer by layer in this case. Okay, so the next technology is so-called laser powder bed fusion. And in this technology is mostly used for metal additive manufacturing. And in this case, you have a printing substrate, and then you spread a layer of powder onto the substrate, and then you select and fuse the region you want to melt. And then once you finish a layer, you lower down the printing substrate, you spread the second layer, and then you melt the second layer. So this allows you to build a 3D object layer by layer. And the last technology is called laser directed energy deposition. It's also used mostly for metal additive manufacturing. So in this case, you have several powder feeding nozzles, and then the powders are fed through the nozzles, and the nozzles are aligned axially with a laser beam in the center. So in this case, once the powder exits from the nozzle, they will be melted by the laser beam onto the build substrate. So this allows you to deposit metals layer by layer. And in a typical laser metal additive manufacturing process, either laser powder bed fusion or laser directed energy deposition, there are two types of processing parameters that you can tune to get high quality materials. The first type of processing parameters are related to the laser building process, such as laser type, laser power, the atmosphere gas, and the printing substrate temperature, and the laser scan patterns, laser scan strategies, the layer thicknesses, and so on. And on the right side, these are the the second type of processing parameters, which are related to the material properties, such as the viscosity of your material, the surface tension of your material, thermal conductivity, laser absorptivity, and the powder shape, the powder physical properties such as the melting temperature and so on. So in a sense, when you try to build a 3D component from a specific alloy, so the material properties are the properties that you don't have a good control, right? For example, if you want to build aluminum silicon magnesium alloys, so those physical properties are almost fixed. You cannot really tune it. Whereas the first column of processing parameters are the parameters that you can tune to optimize the process to get high quality build. So and then we have, the community has studied this process intensively. So now there are several parameters that people typically found very useful to tune to improve the build quality. So the first is the laser power, the second is the laser scan speed, and the third is the hatching spacing, and the fourth is the layer thickness, and the fifth is the laser beam size, and the last one is a laser scan strategy or laser scan pattern. So there are two often used scan strategies. One is so-called chessboard, and the second is continuous. The chessboard simply means you divide the entire build area into many small squares so that you don't need to scan from the first, from the start to the end in a continuous pattern. So in this case, then people have developed a very useful criteria, so-called density criteria. So in this case, the volumetric energy density is defined as E equals to the power, laser power, divided by the volume of the melt pool, which is given by the laser scan speed times the patch spacing times the layer thickness. So this volumetric energy density, VED, simply means the energy density you input in the melt pool. So that's why it's given by the laser power divided by the volume of the laser melt pool. And a lot of studies in the literature have revealed that there's an optimal volumetric energy density window. And within this window, you can build very high quality components with the relative density close to almost 100%. Whereas if you go beyond this window, for example, if you use a very low volumetric energy density, then you will have a low relative density, which means you will have a high porosity. On the other side, if you use a very over high volumetric energy density, you will also have a low relative density. Also, means you have high porosity. So on the left side, if you use over low volumetric energy density, then the increased porosity arises due to lack of fusion. On the right side, if you use an over high volumetric energy density, then you bring another type of defects, so-called keyhole pores. Okay, so in the next few slides, I will explain how these two different defects are, what these two defects are, and how we can quantify those defects. So the first type of defect is, as I said, so-called lack of fusion defect. And in this case, you have a low volumetric energy density. In this case, essentially, when you melt the powder, the melted pool penetration depth, the laser penetration depth is not sufficient to penetrate into the previous built layer. So in this case, if you define a lack of fusion coefficient, which is given by the laser penetration depth D over the built layer thickness T. So in this case, basically the penetration depth over T, the value is not large enough for you to penetrate the entire melt pool deep enough to be able to bond with the previous layer. So this at the bottom, you can see a typical plot of lack of fusion coefficient LF versus the energy density input. As you can see, with higher and higher energy density input, your laser penetration depth will be increased gradually, and this will allow you to achieve a higher and higher D over T. So then the porosity will be reduced. On the right side, you can see the porosity is a function of this lack of fusion coefficient. So it scales indirectly with this LF, right? So with increasing this LF value, then you have lower and lower porosity. So basically, with increasing energy density, you will get higher energy density input, right? So this will allow you to achieve a higher penetration depth. So this will help to get a better bonding between neighboring layers, essentially, to avoid the lack of fusion defects. And the lack of fusion defects often happens at the interlayer regions. So the regions that is at the between the neighboring layers, right? So and those lack of fusion defects are often appear to be linear shape or like line shapes, right? So if you look at the optical mic graphs, here on the left, you can see those lack of fusion happens parallel to the interlayer, And if you look at those lack of fusion pores after fracture of the specimen, you will see that those lack of fusion pores often appear to be linear shape. So it's very harmful for the mechanical properties of the 3D printed metals. And these pores are often irregular, linear in shape, and very large often, and between 100 to 150 microns. So now let's look at another type of defect, so-called keyhole defect, right? So keyhole defect, in contrast to lack of fusion, which is due to an over low energy density input, keyhole defect arises due to over high energy density input. So in this case, you input too much energy, laser energy into the melted pool, and then you have an over melting phenomena. And once you have over melting phenomena, the melted pool, some of the melted pool may evaporate, right? The liquid metal may evaporate. So this will lead to trapped gas from the environment. And the trapped gas, once they enter the melted pool, they will form spherical pores. Those entrapped gas will form spherical pores. And typically, these entrapped gases are small. They are between 5 and 50 microns in size, and they are highly spherical. So if you use 3D computed tomography technique, CT tomography, to image those keyholes, you'll see that those keyholes are often highly spherical, and they are in a size range of 5 to 50 microns often. So the last defect, or a very often phenomenon that we need to pay attention in 3D printed metals is the so-called thermal residual stresses. So this happens due to cyclic heating and cooling process. So when you are heating the material, so if, for example, when the laser is melting the powder, you form a melted pool, right? So this local region is very hot. However, the surrounding material as well as the substrate is cold. So the melted pool is hot and it tends to expand, whereas the surrounding material and the substrate tends to be cold and constrain the expansion of the melted pool. So this will induce a compressive residual stress onto the melted pool, right? And on the other hand, after you melt the melted pool, and then the component undergoes, the melted pool undergoes cooling process, right? So the melted pool wants to cool, wants to contract, whereas the surrounding material and the substrate don't allow it to contract or to shrink, right? So this will induce a tensile residual stress, right, to the melted pool. So in this case, this thermal residual stresses happens cyclically because the laser processes the material, cyclically, right? So in this case, this will induce very large thermal residual stresses, and we often need to apply some post-processing procedures to release some of the residual stresses. So this post-processing often is employed by heat treatment. So now, so far, I have briefly gone through the very basics of additive manufacturing technologies. So in the next slides, I will talk about some specific examples where we can use those laser additive manufacturing in particular to process the complex alloys, which I have shown you earlier that are difficult to process by conventional manufacturing processes such as casting, right? So you will see that laser additive manufacturing indeed give us ample opportunities to process these complex alloys with engineered structures and often improved mechanical properties. So during laser additive manufacturing, the transient laser powder interactions often induce very large thermal gradients and high cooling rates. For example, on the right side, you will see a plot of cooling rate versus thermal gradient for conventional casting versus laser additive manufacturing. So in this case, you will see that the laser additive manufacturing exhibit several orders of magnitude higher cooling rate and larger thermal gradients compared to conventional manufacturing such as casting. So this will allow us to achieve far from equilibrium solidification microstructures as well as unusual material properties. So in a sense, laser additive manufacturing provide us with new opportunities for material design. So in our research group, we have studied a wide range of metal alloys by laser additive manufacturing to achieve unusual material properties. For example, we have studied stainless steel, where we can control the dislocation cell structures to get a high strength and high ductility. We have also studied the high temperature superalloys, where we can control the location-specific precipitates to achieve high temperature strength and high temperature creep properties. And we have also studied metallic glass matrix composite, where we can tailor the spatial distribution of the secondary crystal dendrite within the amorphous matrix so as to achieve a high strength and high ductility. Very recently, we have also studied the nanostructured eutectic high-entropy alloys by laser additive manufacturing. So in this workshop, I will, for the interest of time, I will focus on the eutectic high-entropy alloys. I think most of us may be very familiar with eutectic phase diagram. So for a conventional eutectic alloy, such as tin lead binary eutectic alloy, if you melt this alloy and then you cool it down slowly, you will get a so-called laminar eutectic colony structures, right? Colony structures. Within each colony, you see dual phase laminar structures. And now with the complex alloys, such as this aluminum, cobalt, chromium, iron, nickel, quinary eutectic high-entropy alloy. So if you do casting, you will also get laminar eutectic colonies. And within each colony, you will see very interesting dual-phase microlaminar structures and composed of FCC and BCC microlaminae. And the laminar size are about a few microns. And very interestingly, both laminae are highly ordered. So, if you can see this EM selected area electron electron diffraction pattern, where you can see those extra lattice spots that corresponds to the L1, 2, and B2. So due to the combination of the dual phase microlaminar structure, you can get very good balance in terms of strength and tensile ductility. So now let's look at the laser additive manufactured eutectic high-entropy alloy for the same composition. So if you look at the laser additive manufactured eutectic high-entropy alloy, you can see that this alloy exhibits excellent printability. You can print it into complex geometries such as the lattice structures and some gears. So you can also see very typical laminar eutectic colonies tends to grow from the melt pool boundary towards the center of the melt pool. And if you further zoom in into the microstructure, you can see that the microscale eutectic colonies tend to exhibit different crystal orientations, and the eutectic colony are about a few tens of microns in size. And if you further zoom in, you can see that within each eutectic colony, you will see dual phase nanolaminar structures. And the BCC nanolaminae are of about 60 nanometers in average thickness, and the FCC nanolaminae are about 150 nanometers in thickness. So these laminar thicknesses are order of magnitude smaller than the microlaminar structures that I showed you earlier in the previous slide for conventional cast material for the same composition. And now, if you further zoom in, you will see that there's very interesting elemental distribution within the dual phase nanolaminar structures in the 3D printed eutectic high-energy alloy. The FCC nanolaminate tend to show very uniform elemental distribution. And in contrast, in the BCC nanolaminate, if you zoom in, you'll see very interesting spinodal decomposition-like features. And this feature is composed of two different regions. One region is rich in nickel and aluminum, and the other region is rich in cobalt, chromium, and iron. So this gives you bicontinuous spinodal decomposition-like features. And this table gives you a more detailed description of the compositions of the dual phases in as cast sample versus 3D printed sample. As you can see, in the 3D printed sample, the elemental distribution between the elemental partitioning between the two laminae are less. The elemental distribution, the elemental partitioning is much less than that in the as cast sample. So, for example, in the as cast sample, you can see the FCC L12 laminate has only 6 atomic percent aluminum, whereas the BCC B2 laminate have 38 atomic percent aluminum. In contrast, the 3D printed sample shows much less elemental partitioning between the dual phases, right? So the much less elemental partitioning between the dual phases will lead to the observed, disordered solid solutions as opposed to the ordered phases such as L12 and B2 in the as cast sample. And also the much higher cooling rate during laser additive manufacturing will help us to achieve highly refined laminar sizes to nanoscale as opposed to micro scale in the as cast sample. So due to those different features, we can achieve very high strength and ductility in the 3D printed sample, as shown by the tensile stress strain curves. So the red tensile stress strain curve is a 3D printed sample. You can see that the yield strength is above 1.3 gigapascal, along with a very large uniform elongation. And this yield strength is more than twice of the as cast sample. And in the meantime, with enhanced yield strength, the uniform ductility is also simultaneously enhanced compared to the as cast sample, which is the black curve, right? So in addition, by applying post-heat treatment, such as annealing at 600 degrees C for 5 hours, we can achieve a very high ultimate tensile strength, about 2 gigapascal, with still very large uniform elongation above 7%. And by annealing at 800 degrees C for 1 hour, we can still maintain a high yield strength above 1 gigapascal with much higher uniform elongation, almost above 20%. So these allow us to achieve a broader range of exceptional mechanical properties compared to other 3D printed metals such as steels, titanium alloys, or nickel-based superalloys, right? So these 3D printed eutectic high-energy alloys can allow us to achieve properties really well surpasses those of conventional 3D printed metal alloys. So now let's look at the general consideration when you consider laser additive manufacturing. So there are certainly a lot of pros that help laser additive manufacturing to stand out compared to conventional manufacturing. For example, you can have a very large build dimension, you can build a very large components, and you can build a variety of materials. For example, I have shown you steels, nickel-based superalloys, titanium alloys, high chip alloys, very complex alloys, right? You can build them easily by laser additive manufacturing. If you use conventional casting, as I said, you may end up with a lot of defects, pores, very significant dendritic versus interdendritic segregations. And laser additive manufacturing is also a very fast 3D printing process. And this gives you an opportunity to build highly complex structures for native shaping, right? I show you the gears, the lattice, lightweight lattice structures, and also together with very excellent material properties, right? On the other side, we also need to keep in mind there are some cons that we need to remember, for laser additive manufacturing technologies. Certainly, there are some residual stresses that we need to consider, and as you build larger and larger components, these residual stresses may build up, and for at some point you may need to apply post heat treatment to release those residual stresses. And there are some defects, although those pores may be much smaller than the casting pores that you often see. So those pores are very small pores, such as lack of fusion, keyholes. They're some, most often they may not degrade your tensile or compressive properties too much, but they may play a key role in fatigue properties of many structural components, right? And we also need to keep in mind that because the laser has a beam size of about a few hundred microns, so we have this limitation in terms of resolution. We can only achieve hundreds of microns resolution and surface finish. If you need to have better surface finish, you may still need to apply a post process. And one last thing is the process is expensive compared to conventional manufacturing, such as CNC machining, right? So now, in which scenarios I should consider laser additive manufacturing, and in which scenarios I should consider conventional manufacturing? So to answer this question, I want to show you a very good diagram where we can see two curves. One curve, the black curve, is for conventional manufacturing, such as CNC machining, and the plot is cost per part versus complexity or customization. So in this plot, there are two curves. One curve is traditional manufacturing. The other red curve is for additive manufacturing. So within this curve, you can see that for traditional manufacturing, the cost per part increases exponentially as you try to increase the complexity of the component, right? So which means if you want to build really complex geometries, such as the turbine blade in aerospace, so it really takes a fortune to machine it in the machine shop, right? So in this case, the manufacturing cost can be very high, whereas for additive manufacturing process, the cost to build a square bulk component versus a turbine blade is almost the same, right? So this additive manufacturing, the red curve, the cost per part almost stays constant with increasing the complexity or customization for your part. So in this case, certainly there will be a crossover of the two curves. So in the region where you want to achieve high complexity or high customization, then additive manufacturing will stand out compared to traditional manufacturing. So this is where the region you want to use additive manufacturing. And luckily, with the advancement of additive manufacturing, the processing cost and the design cost has been increasingly, or has been readily decreased over the years. So now the cost for additive manufacturing keeps decreasing and decreasing. So this means the space to achieve to get the extra complexity and customization is the space becomes more and more enormous, right? So you can actually get this extra benefit for free, basically. So with that, I want to summarize my talk. In this workshop, I have shown you, I have given you a brief introduction to additive manufacturing technology, and then I used several case studies to show you how additive manufacturing enables processing of emerging complex materials with engineered structures across multiple length scales, and this will really give us good opportunities for new material design with unprecedented material properties. So if you have any questions, please feel free to reach out to me. You can email me. My email address is wenchen@umass.edu. You can also browse my group website to learn more about additive manufacturing technologies. Thank you.